Okay, so what we have seen yesterday was, we derived an expression to see the density of states variation in the case of a three-dimensional system, which looks like this. So a macroscopic so the density of states to phi, so you what is that? Okay. Now we need to see what happens for the 2D, 1D and the zero-dimensional systems. Before that, the density of states variation for a three-dimensional bulk material, in reality, where would you encounter this kind of a behavior? Of course, we talk about doping in semiconductors or doping in material systems, and doping has effects in electronic band structure and also the electronic density of states. Okay, so the valence and conduction band edges for a typical semiconductor, say, and if I have okay, that's your Fermi level. Right. Now, so we can something called GVE. So the energy scale is here, and the density of states. In each case, you have the valence band edge and the conduction band edge. So in a three-dimensional case, if you are asked to represent the density of states in both the cases, see, because doping certainly affects the number of carriers in a semiconductor. Okay, so you can create majority and minority carriers in a semiconductor, and that can be represented in a nice way. First of all, that's how you show the density of states variation on the conduction band edge side and the valence band edge side. Okay. Now you see, this exactly replicates what you have drawn there for a three-dimensional case. Density of states as a function of energy. Now, if this bulk semiconductor, it's a 3D macroscopic semiconducting material, if the size of the semiconductor is cut down, if you make a two-dimensional material out of this three-dimensional semiconducting system, what would happen to this nature is very important to be observed. Then the one-dimensional case and the zero-dimensional case. Okay, just to complete it, we normally also look at the, we have seen the Fermi-Dirac distribution function So you can also plot the occupational probability in both the cases, and you can also plot the carrier density. So you certainly know that what we are representing here is an intrinsic semiconductor case where you have the Fermi level lying in the middle of the forbidden gap between the valence and conduction bands, right? And these are the electrons, and to be more precise, we don't fill this up. To show the presence of holes. Okay. So in terms of probabilities, there's equal probability of equal number of electrons and holes in the case of an intrinsic semiconductor. Okay, and there are two aspects here. Now you have an intrinsic semiconductor, you reduce its dimension, go down to the 2D, 1D and 0D states and see what happens to the density of states, and you need to also see what happens to this occupation, right? Case 1. Case 2, you do the same thing with respect to a doped semiconductor. So you know what happens if the semiconductor is doped now, is it not? So what happens? If you are making it an n-type semiconductor, in the case of an n-type semiconductor, okay, and correspondingly, of course, since we are still dealing with the three-dimensional bulk semiconductor, n-type or p-type, the density of states, look like this. There's no problem. But what about the carrier density? How do you represent the carrier density in the case of a semiconductor, doped semiconductor, where the chemical potential has been shifted close to the conduction band? You see what happens in the case of a doped semiconductor. As you make it an n-type semiconductor, you are creating the donor levels, and in the case of a p-type semiconductor, you are creating acceptor levels, right? So if you look at the carrier density in this particular case, what you will see is so there electrons become the majority carriers and holes become the minority carriers. And if it is the other case, if it is a p-type case, you will see this level coming close to the valence band edge, right? You have the acceptor levels, and this scenario is reversed. You have a minority band consisting of electrons and the majority band consisting of holes. Okay. But in all these three cases, we need to see what happens in the low dimensionality, with respect to what is the effect of low dimensionality on the density of states. Okay, good. So you can also plot the occupation in each case. What is it here in this particular case? F of E. And what happens to the probability distribution function in this particular case? 1 minus f of E. So in terms of the density of states, how can we write that? Is it okay? Good. Okay. Then of course, electrons and holes you can get to know about the carrier density, nature of carriers by Hall effect measurement, and the nature of carriers can also be obtained by Seeberg measurements. But if one needs to find out the electron carrier density, the number of electrons and holes, remember these are all, when we talk about the carrier density that you obtain from the Hall measurements only, it's only the mobile carriers. You don't get the number density, that is the total number of electrons present in a system. That can be evaluated easily from the density of a material, right? So from Hall measurements you can get the information about the nature of carriers and also the carrier density. And when you say carrier density, these are the actual mobile carriers. Okay. Now, so let's go to the two-dimensional case. Okay. So I thought I'll put it in such a way that first you need to understand what is a two-dimensional system. Of course, I told you this before. You take a block of a macroscopic system, and if you just slice it, right, and if the thickness of this slice is within the nanoscopic range, you call it a two-dimensional system, a quantum well. But what you need to understand is, in practical terms, what is a quantum well, right? That's what I'm trying to show you here. Okay, a quantum well. I gave this example also earlier. Now, if you have a sheet of conductor, and if the thickness of this sheet is within 100 nanometers, you are expected to see confinement along the z-axis, along the thickness direction. Now, in a macroscopic bulk, there is no confinement. Okay, but now we start seeing confinement in one of the dimensions, that is a thin conducting sheet whose thickness is in the macroscopic nanoscopic region. Okay. Okay, that's what is how a two-dimensional quantum well is represented. I'll also tell you where these quantum wells are used. Okay. Now we can define the energy states in terms of two-dimensional wave vector kx ky, where E is equal to, right, E kx ky. Okay. But we are now because you have the free energy relation holding good in the xy plane, right? The carriers are free to move along the x and y axis, but the confinement is along the z axis. Okay. Now, we'll come back to this particular point a little later, but I would like to mention this here. I showed you the way the Brillouin zones are formed in a crystal, right? The first Brillouin zone, the second one. So we define the first Brillouin zone as the zone with limits from pi by a to minus pi by a, and these zones are appearing because of the confinement where your k vector takes values corresponding to n pi by a. We are clear about that. So you have the first, second, third, etc. Brillouin zones. Now, when we talk, see, this is just to give an analogy of the actual confinement with respect to two-dimensional systems. Now, when you look at this picture on the right side here, you have the first Brillouin zone, the second one. Okay, of course, in 3 dimensions it looks a little more complicated. Now, imagine if of course this is the two-dimensional case we are talking about, and if a carrier is moving from one zone to the other, right, it certainly experiences some kind of potential at the boundary. The same kind of potential that we are talking about when an electron is propagating in a crystal or a solid, right, it experiences the periodic potential defined by the lattice. So now for the carrier to move from zone 1 to zone 2, it has to overcome this potential. Then only it can propagate from zone 1 to zone 2. So it's exactly equivalent to creating a two-dimensional quantum well, an artificial two-dimensional quantum well. Now, so I make a very thin layer, right, sandwiched between two layers whose band gaps are different from the intermediate layer, which I call the quantum well. Now, the whole idea is I want the carriers to get confined in the intermediate layer. Okay? So, the boundary conditions apply there. So, as the carrier moves from the top layer towards the bottom layer or vice versa, the carriers experience a huge potential at the boundaries. And that potential that that the carriers experience in artificially grown layers is equivalent to what happens in the case of an electron, a carrier moving in between these zones. Exactly, there is a nice correlation between these two. Okay. Now, so your kx is equal to ky is equal to 0 in the 2D Brillouin zone, and the band edge mismatch simply implies that both electrons and holes are confined. They experience confinement, which is the quantum confinement in a crystal. You know, now we know that. You see that the so-called periodic lattice we are talking about. See, what we are applying here is I can't go into all those details of the Bloch theorem, right? In the Bloch equation, or in simple terms, the Bloch function representing what is called a Bloch wave. A Bloch wave is a periodic wave in a crystal when, you know, a periodic potential is multiplied with a plane wave, you get a Bloch wave. And Bloch wave arises because a typical example is a particle moving in a periodic lattice. Shows a wave-like nature, and this nature can be represented by what is called a Bloch wave. And what is the best example? There is no better example than considering an electron moving in a crystal. So if the crystal is periodic, right, you can consider a periodic Bloch wave function. It's as simple as that. So okay. U is the potential function, the plane wave, and what you get is a wave function representing the Bloch wave. Okay. Now you can apply the Bloch theorem formalism to the 3D, 2D, and one-dimensional cases also. That's what we are trying to do here in a simplified way. Now the allowed energy levels of the electron in this case will be that, you know that, because now since the confinement is happening along the z direction, right, the Schrodinger equation can be written in this form, is it not? Yeah. So a typical two-dimensional quantum well is shown here. So these are three layers, so you can call it a multi-layer system where you have gallium arsenide, which is the sandwich layer, and the layers on the top and bottom are aluminum gallium arsenide. Okay. This represents a typical quantum well structure. So when we say a quantum well structure, it is a two-dimensional quantum well, obviously, right? Okay. Now you see, if you look at the band edges, so this is this direction is the growth direction, right? So I have the base here, I grow the first layer, second layer, and third layer. So this is the growth direction, right? I have a substrate on which I have grown the first layer, the second one, and the third one. So this is also Z direction. Okay. Now, the thickness of this layer is extremely small. Now these are all ultra thin layers with thickness of the order of 5 to 10 nanometers. I'll also tell you where such layers are used. Okay. Yeah. So this is what you see, the variation of the conduction and valence band edge energies. You look, the moment you see a band picture like this, okay, of course the energy scale here, growth direction, energy scale in this way. The moment you see a band diagram like this, you should realize that, look, the band gap tuning has happened. So this is, in one way I was talking about the band gap engineering. Now, this shows that I have two layers and an intermediate layer having, different band gaps. Now, what is the advantage of constructing such a two-dimensional layer? So these kind of layers are used for the fabrication of, so-called the quantum cascade lasers. Okay, so yeah, you see that picture on the left side? This is how the structure looks like. This is a high-resolution transmission electron microscope image, which shows, alternative layers of different materials. Always remember, if I have alternative layers of different materials, I call it a heterostructure, two different materials. Okay, and if the layers correspond to the same material, I call it a homoepitaxial structure or a homostructure. Because so if I have gallium arsenide, two layers of gallium arsenide, one is p type and one is n type, I can call it a homoepitaxial structure. Epitaxy corresponds to the crystallinity of the layers. A highly single crystalline layer of n type gallium arsenide and the single crystalline layer of p type gallium arsenide, I call it a homoepitaxial layer. But if I am getting two different layers, gallium arsenide and aluminum gallium arsenide, so you can call it a heterostructure. If I am depositing gallium arsenide as one layer and say gallium nitride as another layer, it's a heterostructure. Okay. So what's the idea of creating such structures? See, that's how, again, a magnified image of this transmission electron microscopy. See, it's not easy to create such layers. You have, a number of these alternating layers, right, with extremely small thickness. A sketch of these layers is shown here. So this is the actual transmission electron microscopy image of gallium aluminum indium arsenide and aluminum indium arsenide quantum cascade laser structures grown by a very sophisticated technique called molecular beam epitaxy. Okay. So for layer widths of 10 nanometers or below, both electrons and holes experience significant quantum confinement effects. So the whole idea is to create these structures in order to make the carriers experience quantum confinement effects. So you can look at the physics of quantum confinement, and also there are several applications. Now, just before that, you see this is a real masterpiece. So you have a substrate here and you start growing all these layers. See, the interface here plays a very crucial role, right? Because especially when you are growing structures of 2-3 different materials, right, there is no guarantee that crystallinity exists at the interface. And how do you look at that? So you need high resolution electron microscopy. So I just expand or magnify this region and see what you see here. This is called the interfacial epitaxy. You don't see any defects at the interface, right? You see periodicity of the lattice continuing from this layer to this layer to the other layer. So when you are looking at fabrication of lasers, you need these kind of interfaces. So what is required? It requires really sophisticated growth technique, and also a technique that gives you information about the quality of the interface. a high resolution microscope. Now of course you have in situ techniques to actually monitor the way each layer, each unit cell is growing. Okay, we'll see some of them. So this is the position of the upper interface and the position of the lower interface. You see you can ascertain that the quality of these interfaces is very good. Okay. So again, where do we use such interfaces? Now you see this is a complicated multi-layer structure of a laser. Right. Now I have here a p-type semiconductor and an n-type semiconductor and the intermediate layer, exactly the kind of the structure that I have shown in the form of a sketch in the previous slide. So the whole idea is this. See, we can create what is called injection luminescence when you have a p and n junctions. Okay? When you have a p-type material, n-type material, if you make a p-n junction sandwich between these two, you can pump carriers from one side to the other, and when carriers recombine, the recombination can give rise to light emission. Okay, this is a simple way of getting light emission. But now this recombination is done in a quantum well. So imagine I have two AlGas, aluminum gallium arsenide layers, one doped in such a way that it becomes a p-type aluminum gallium arsenide, the other one is n-type aluminum gallium arsenide. Now the intermediate layer is gallium arsenide. So the band gap of gallium arsenide is little smaller than that of the AlGas. So what you do is, you've seen the band gap structure already, right? This of course is the growth direction, right? So you can, when carriers move from one edge to the other, you ought to see confinement. So the whole idea is when carriers are pumped, they're not made to recombine directly, but they're pumped into this intermediate quantum well layer. Because of the narrow band gap of this sandwich layer, the carriers are trapped there because it's a quantum well. When the carriers are trapped there, there's no way the carriers come out of this potential barrier easily. And that leads to recombination of p and n-type carriers, and under certain conditions this recombination can lead to the lasing action. No, it's a beautiful way of constructing a laser, and of course depending on the number of quantum well layers, depending on their thickness, you can actually tune the light emission that results in such quantum well structures. Okay, now what happens? Of course we need to see what happens to the. So this is a basic definition of a two-dimensional structure. Of course you can always say it's simply, you start with a three-dimensional macroscopic bulk and take a slice out of it, right? And it's called a quantum well. But in order to call a thin slice a quantum well, the effect of that quantum well is this one. You make the carriers to confine, and something happens at the boundaries. Okay. Now you see this. Now we start with where we left yesterday. We can define the density of states function dE such that the number of allowed states, you call it dN, between energies E and E plus dE is given by, right? Now I would like to also represent this in terms of the number of allowed states in this energy range will depend directly on the number of states whose allowed wave vectors also fall in that range, which means your dE dk, dE is nk dk. You will also see this represented as n of E in some books, but since I started giving this notation, we will continue with that. Okay. Now, nk is the density of allowed k points in the system. Okay. Now, if you rearrange this equation too, let us write it this way and keep it. Okay. Of course, we have if I take a derivative of this, right, we have one more equation here. Now, here for all practical purposes, I would like to represent this mass as m star, which is the effective mass of the electron. Okay. Okay. Good. So that's what I have done here. Now, what is the purpose of doing this? See, if the energy is changing rapidly with the wave vector d by dk, then there will be fewer states in a given energy range than when this d by dk value is smaller. Okay. Now, yeah. So you get the expression. Now, what you do is I take this this equation and substitute this over there and see what happens. So your d becomes that's what I have here. Okay. So there is always an NK dependence on the the dimensionality of the structure. When NK depends on the dimensionality, so does D. So it's as simple as that. Now, quickly, if you just consider a what is called a two-dimensional grid, like what is shown here in the picture. Okay. Now, in the Brillouin zones, in the first Brillouin zone, as the second Brillouin zone, right? If you are asked to plot the electron energies, you always get circles of constant energy. Okay. Now, these circles of equipotential circles, they get distorted as you go towards the edges, and same thing should happen here also in a quantum wave structure. That's why I said there is a good analogy between these two. Okay. Now, let's look at a grid like this, which we call it a reciprocal lattice. Even if you don't know what a reciprocal lattice is at this point in time, don't worry. Okay. Okay. Now, this grid represents the allowed k points, and these k points, one point I call it represented by 2 pi n by L and 2 pi p by L, where n and p are some integers. Okay. So, the allowed k points form a reciprocal lattice associated with a two-dimensional crystal of size L square. Okay. Now, the two circles here of radius k and k plus dk describe the contours of constant energy. So, with E is equal to h square k square by 2 m star. So, exactly that is what you see in the first Brillouin zone. You have contours of constant energy, and the circles get distorted as you move towards the boundaries. Okay. Now, in say n dimensions, each k point occupies a volume 2 pi by L to the power n. So, the number of k states per unit volume of k spaces is simply 1 by of this 2 pi by L to the power of n. Okay. Now, we have two allowed electron states per K space, right? So these values are, we call it the spin up and spin down configurations, right? So 2 allowed electron states per K values, and this gives a value of keep that. Now you also substitute this and get that equation. Okay. Now, what is the area between the two rings in the two-dimensional space with radius k and k plus dk? What will be the area there? It's what? 2 pi k dk, right? Right. So you have the area there, and what now? The number of allowed states between k and k plus dk, that is d and k is given by. So you have the area there now. Easy to get. This goes something like this. Your d and k is this value multiplied by now once you have it, now your nk is kl square by pi. That's what you get from this equation. Now if you substitute this into this equation, we find that the density of allowed states near a band edge in a two-dimensional structure of area L square goes as m star by pi L by h cross whole square. What is the striking feature in this particular equation? Because you can just write it in this form also, 4 pi m star by h square. We can go through in a similar manner and get the corresponding equations for the one-dimensional and two-dimensional case, zero-dimensional cases. Okay. We have seen this first. For the three-dimensional case, the density of states goes as root of E, and this is the equation for the two-dimensional case. For the one-dimensional case, the density of states varies as 1 by root of E. It's for the 3D case, it's root of E. For the one-dimensional case, it goes as 1 by root of E. We can plot all these different natures and see, now obviously from the three-dimensional case, the 2D case is different, the 1D and zero-dimensional cases are already different. That means if you plot density of states as a function of energy for all these three cases, you will see different types of plots. Okay. Now, one of the striking features is the two-dimensional density of states, interestingly, does not depend on energy. There is no dependence of energy. Okay. And if there are a number of confined states within a two-dimensional quantum well, the two-dimensional density of states at any particular energy is basically the sum over all the subbands below that point. Okay. So you can represent it in a generic way in this manner. Okay. The summation a square m by pi h square, h cross square, theta e minus ei, where theta is the unit step function. See, we can do much more critical mathematical analysis to reach this equation, but at this point in time, we don't have to worry about it. what I want to show here is the dependence of density of states, on various factors. One striking feature that you see from this equation is, in the case of the two-dimensional system, the density of states does not depend on energy. So, which means when you plot now DOS as a function of energy in the case of a two-dimensional system, that's what you see, right? So, it's like a step-like behavior, okay, because your density of state, this is rho E is also a symbol used for representing density of states, is proportional to m star by pi h cross square, which is a constant, but it can be seen that in a regular two-dimensional case, with the example that I have shown earlier, the steps are of equal height, the heights are equal, okay, occurring at typical different subband minima. However, the spacing is not equal, okay. The step size is equal, the steps, but the spacing is not equal. Okay, you can find out why that happens. Okay. Now, when you come to the one-dimensional system, where the density of states goes as 1 by root of E, this is what you see. The one-dimensional system, the examples are, these are, you can call them quantum wires. In a one-dimensional system, you have two of the dimensions in the nanoscopic regime. So, the density of states shows this peculiar behavior, and in the case of the zero-dimensional system, the density of states versus energy, it's almost like it looks like a delta function. That's what it is. It's very interesting, right? See, to summarize now, if you start from a three-dimensional bulk system and you start cutting down its size. Now, I take a block of a three-dimensional material and take a slice out of it, I get a quantum well. Few more slices, I get a one-dimensional quantum wire, and further cut it down, you get a quantum particle. What is happening in all these cases is, we are actually manipulating the density of state, the way density of states varies as a function of energy. This is amazing, and in order to explain the changes that are happening in physical properties, this is the easiest way to do. Obviously, when the density of states as a function of energy change, then the physical properties have to be affected. That's the overall summary. Now, you start with a cadmium telluride particle, cadmium selenide particle, and then it starts showing luminescence in one spectral range in bulk form, but in nano form the luminescence characteristics change. That's because the overall density of states is affected, right? Is it not? So this is the only convincing way to say that it is the electronic density of states that are affected, and once the electronic density of states are affected, you start seeing changes in the physical properties. That's the reason why I said different systems attain quantum confinement at different length scales. That's the reason why we define this 1 to 100 nanometers range, because certain systems now. That's the reason why I kept telling that, look, you have a macroscopic bulk material in the form of a block, a cube, and then you get this cube down to smaller cube dimensions, right? You will start seeing the density of states variations only at a specific dimensionality and below that value. Okay? It's convincing or not? Good. Now, okay, so look. Now, I plot all this for a semiconductor. Now, it's easy to do it, we understand this. Now, density of states versus energy varies like this for a bulk system. So, Now you also know the reason why this plot is plotted this way in the case of semiconductors. And now if you have a two-dimensional quantum well of the same semiconducting material, right, what happens to this? This starts showing a step-like behavior. Is it not? Now, if I have the 1D case and then the 0D case, you see how the variation happens. It's all there. So we can do all this by calculations for a given system, but doing experiments is not so easy, right? Density of states. How do you find out the electronic density of states? You have to use photoelectron spectroscopy, and photoelectron spectroscopy has to be done as a function of temperature. It's done. It's being done now. It's all these things are all such nice experiments are available now. Okay, good. So now I have we define Lz, Ly, and Lx are the confining dimensions. I, j, k is equal to 1, 2, and so on are the quantum confinement numbers. Kx, ky, kz are the wave vector components along the unconfined directions. M star is the rest mass, effective mass, and if we assume zero of energy at the confined layer, the conduction band edge. Now, how do we represent the energy equation for all the three systems? If we do that, we have completed the story on density of states of 3D, 2D, 1D, and 0-dimension systems. And then of course you can do lots of problems related to this formalism. Okay, so write the allowed energy states of the confined electron in a quantum well. So how do you write that? Or if you come across an equation like this, immediately it should strike you that, look, this is the equation that represents a quantum well. So it is Ei kx ky. Now in a quantum well, kx ky are the k states along the x and y direction where there is no quantum confinement, right? So you will have a free electron energy term and the term corresponding to the confinement. You have h cross square k square by 2m term, and in the other case your k taking definite values. That's it. You have to write this for all the three systems. So you have the first term which goes as h square I square 8 ml z square. The second one is, that is the confinement term along the z axis, is it not? And the second one is the normal, the free energy term, h cross square by 2m k square. K square is kx square plus ky square, because in the xy plane there is no confinement, only along the z axis you have confinement, right? So that represents, the second term represents the free carrier movement along the xy plane, right? So this is a equation that gives allowed energy states in the case of a 2D system where you have confinement along one dimension. Okay. Now, similarly, you write down the expression for the allowed energy states of the confined electron in a one-dimensional case. You have now a rod, a nanotube, a nanorod, a nanofiber, where two of the dimensions are in the quantum confined state. So how does the energy expression look like? So the confinement is along two directions. You can write the free energy term only along one dimension, and so you have your Eij is kx, right? If x is the length dimension which is still in the macroscopic regime, and the confinement happens along the y and z directions. And this is again simple, no? So the confinement term along the two axes y and z, h square by 8m I square by Lz square plus j square by Ly square, plus the free electron movement that happens along the x axis, which is h cross square kx square by 2m or 2m star to be more precise. Now in all these cases it is better to replace m by m star, the effective mass. Now the last thing is write down the same thing for the allowed energy states of the confined electron in a zero dimensional system, that is a quantum dot. So now you have the confinement in all three directions, in all three dimensions rather. So it's simply, this is the term, you have h square by 8m I square by Lz square j square by Ly square plus k square by Lx square. So confinement along all three dimensions. There is no free energy term here, right? So it's so again so the summary of all this is shown there. So the quantum well, the quantum wire and quantum box. Of course, what is it for the three dimensional case? It is simply h cross square k square by 2m. There is no confinement anywhere, right? Good. So see you on Monday. I have a very quick question. This is what you see on the left hand side of the screen is, the simulated probability density distributions of electrons in different states, right, with increasing number of n values. Of course, you can also represent it this way, where the wave function of a 2D well within nx is equal to 4 and ny is equal to 4. Okay. But just take this example. So there is no probability of finding an electron in the middle of the box. How can the electron move from one side of the box to the other side without going through the middle of the box? The probability distribution is, you see, and there is nothing in the middle. How is it possible? So the electron is, of course, moving between the walls, right? It's moving very quickly. But when it comes to finding out the probability distribution, you don't see an iota of probability of finding an electron in the middle of the box. The question is, how does the electron move without touching the middle of the box? You have an answer for this? You get an answer for this provided you do this problem. Find out the probability that a particle trapped in a box of width L, okay, can be found between 0.45 L and 0.55 L for the ground and the first excited states. This will be an interesting problem for you to, of course, it will. I think the same thing will come in the the assignment sheet also, but work it out. So the answer you get here, you can make a meaning out of that only when you look at the the so-called. Can you have any clue? Instead of me giving clues, I think you should tell me how quickly can you do this? Next class, Rika? Yes. Oh, okay. All right.